Okay, so this is the 11th problem in the grind 75. This is lowest common ancestor of a binary search tree. We're given 20 minutes, and so we're going to start the countdown now. Okay, so what do we have? Okay, given a binary search tree, find the lowest common ancestor, LCA, lowest common ancestor node of two given nodes in the BST. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. A descendant of itself. Okay, let's look through the examples. So, okay, it's represented as a list. Our two nodes are 2 and 8. Lowest common ancestor is 6. That makes sense. Let's look at another example. If we have 2 and 4, it's also 2. Okay, that's what it means by a node can be a descendant of itself. And let's see, if we have 2 and 1, how exactly are how is this tree spreading out? So it looks like it's root, left child, right child. It's how you would, oh, well, I guess we don't have to worry about the list representation because we're going to be given this implementation of what a tree is. Left, right, value. Okay, so that's good. Can we assume that there's unique integers? Yeah, all node values are unique. Okay. Number of nodes is at least 2, so this is our base case. And P does not equal, P and Q will exist. Okay, so if the BST has 2 nodes, then we already know that the output will be the first, well, we actually don't know where exactly, well, so we have the root. Okay, yeah, let's think about a general approach to this. So I'm going to look at example 1. Maybe example 2 is probably a little better. So we're going to start out at the root. I think we should traverse until we find one of them. But it seems like we always need to keep track of what the parent is. So maybe we can say how do we know? See, looking backwards in a BST is sort of tricky. So, okay, again, just gonna look at example 1. I mean, and root.right, check if either equal P or Q, maybe. Will that help us in both cases? Well, in this case, P is equal to 2 and Q is equal to 8, and then the root is automatically the lowest common ancestor. So let's see. Say we had like P is equal to 2 and Q is equal to 7. The lowest common ancestor will still be 6. In fact, what if we do, maybe we'll do 4 and 7. Okay, again, lowest common ancestor will still be 6. We can look at the left and right. If either of them equal P or Q, then we would save that somehow. If it equals just one of them, then we'll stop there. But again, we're looking at 4 and 7, right? So we have a root. Left and right does not equal P or Q. So then we recurse left and right. The right equals P. In this case, the left equals Q. And what are we returning? The tree knows the lowest common. So after we make these recursive calls, otherwise we would recurse after calls if left recurse and right recurse are the same. Well, that's not exactly what we want to do. Because when we're going down, we're not going to be returning anything. We're just going to stop. I think we should return ourselves. Yeah, so return current tree node. So if they are not equal, so if the recursion yields some difference, then we just want to return up. We don't even want to return the root. Okay, I think that sort of works. Let's just write out some code to see what this would look like. So first off, we want to check if, see, the root itself might even be. So what if we just look at the root itself? Is it possible? It's not possible that P and Q will both be the root. So if we're just looking at the root, let's say if root dot val is equal to P dot val. Say that's the case. Then, let's see. I'm trying to see how afterwards we would return the top root value, if that's the one, because if we just say root is equal to value and then return root dot val, and that's not going to work if we're recursing and we get down to 4. Would we need to make some sort of separate function? Could we break the logic into 2 pieces, or is that even necessary? So I guess one step is traversing until we find P and until we find Q. But then once we're down there, how do we go back up and how do we maintain our ancestors? So well, okay, we are returning a tree node, it appears. Hmm. So something that comes to mind, which there might be some way to do this recursively in record, is we could just kind of do like a while loop actually. And as we're going down, let's see. I was thinking we would make some sort of hash map where we're keeping track of parents, but let me think about how that would work. So 6 would have, okay, I guess not really parents, but it would be some sort of list in order of closeness to the parent, if that makes sense. So say we'd have like a key of 6 and then an empty list. And for 2, we would have a key of 2 and then 6 as the first value. Then once we go down to 0, we would have, you know, but then that brings in this part where a value could easily be its own descendant. So it seems like so I will want some the int will be so I want to make again I want to make a hash map, but how do I make the list? I want to reduce time as much as possible. I might be thinking this in a bit too complicated way, but I think it would be cool to figure out how this would actually work. And I also want to try to do this without using an array list, because I haven't seen a problem yet that has used an array list. I mean, there will probably be one in the future, but let's see. So, okay, just so we have a complete conceptual understanding, 6, we check the hash map to see if it has any parents. I mean, it has a parent of it. Okay, so it doesn't, we don't check the hash map until we actually get P and Q. But for each node, we are going to be adding an entry into the hash map. And basically, so 6, it would just have itself. 2 would have itself plus 6. 0 would have itself 2. But then how do we remember whose parent is whose? I mean, if we did it the opposite way, where the key was the parent and then all the values were all the children, 6 is the key, and then each time we go down left and right, we add that to. I feel like this is a little more complicated than it has to be. So if we were to just try to do it the way we were originally going to do it, we have to get the least common ancestor, which again could be pretty far back. But I'm trying to think of how we could use recursion to do this. We'd go left, right, left, right. Let's see. Again, we're gonna say, well, let's say it's 0 and 7. Left and right. Okay, I'm going to try the original idea that I came up with and see if it actually works. Root val. Just also do hash map. Is equal to q.val. We'll see. Is that even what we want to do? Again, we just want to get the most recent ancestor, essentially. So we're going to return that. Let's say if it's not equal. So either or. I want to do some kind of comparison between the recursive calls. Which, I mean, what comes to mind is to call lowest common ancestor again. This time we're going to pass in, say, root.left, again p, and again q. And then we're going to do some type of comparison here to lowest common ancestor, root.right, p, q. But what are we actually trying to find out? Because so if we get the p-value, say we get down here and we get one of the values and we get the other value. When this returns from its recursive call, it's going to go up. So actually return. Lowest common answer. But then, okay, so again, match is found for both p and q. We're going to recurse up. If there is no match, then we want to recurse up. If there's finally a match, then we want to return that value. Okay, I think. Let me just. do if that, and we're just about out of time, but that's pretty much what I'm thinking. So I'm just going to think of this from a top-down point of view. So say we're up here, and again, our values are 0 and 7. If the root is either the values we're going to return, otherwise we're going to recurse. Okay, so say recurse this way. If either return, otherwise recurse. We also need root is equal to null. And say we finally get down to here. Same. Not we're going to pass up. Okay, this, I believe this makes sense. I mean, let's see and run the example. Return. Well, so I want to pass it up. Let's say return null. I think null can, I believe null does not equal null. Run it really quick. Missing return statement. Oh, let's see. If none of that's true, let's say we return null as well. Yeah, but let's see if the actual, I don't know if this is actually going to work. Yeah, null pointer exception. Murder is null. So maybe let's put this condition first. Submit. Yeah, we didn't yield the right answer. So say we had 2 and 4. Two and 4, it should be 2. I gave it 6. Okay, I'm going to stop here. I'm sort of stuck as to what the logic was. It never really stuck with me as it should have. And I will take a look at this problem in depth in the solution.